Welcome back, everybody. We're gonna now continue our journey on failure. So in the rest of the time of today, I'm gonna first show you the definition of failure. So what is failure? And what are the different types of failure concerning engineering materials and structures? Afterwards, I'm gonna show you some typical characteristics of each type of failure. And followed by that, we're going to discuss the mechanisms of each type of failure. So this is our coming back from the property to structure again. So we're always going back and forth with these two components, right? And after that, we're going to go as our typical learning strategy from qualitative issues to some quantitative measures. So first, we're going to give you the definition about a few new terms which are related to the material's resistance to against failure. And after that, we're going to show you under what kind of condition or situation does each type of failure occur. And in the end, of course, we study failure for one purpose only, is to avoid it, right? And then I'm going to show you how we're going to use our knowledge and skills to reduce the likelihood of each type of failure. What is failure? So here I'm already showing you one quite significant picture about failure, or to be more precise, it's a fracture of a pressure vessel. I think you probably know what pressure vessel is about, but here we're really looking at a very big one. And this is a test done by the material testing lab at Stuttgart. So it's MPA. And we can see this is failure. And how do you define it? I would like to give the following definition. So failure is a material or component stops complying with the service requirement. So this is a very general and really covers a lot of types of kind of failure that we have discussed. Because failure is always related to a service requirement. If something cannot comply with the service requirement, we call it failure. So here I'm showing you fracture, but you will probably see failure is not always just a fracture. So that is our kind of very nature introduction about failure types. So here I'm giving you a quite comprehensive classification of different types of failures. So let's start with the center. Let me get the pointer here. So we start with failure itself, and a very, very similar term to failure is fracture. I mean, in engineering microstructure world, right? And because these two terms are often mixed, and even for very kind of expert in this field, they also get these two terms mixed. So here I want to give you a clear, maybe not very clear, but that will help you really distinguish between these two terms. So to a certain extent, failure is largely related to fracture. But fracture is, let's say, a subcategory of failure. And fracture can be further divided to cleavage fracture and ductile fracture. So the cleavage fracture is also called brittle fracture. And we're going to use the brittle fracture in the following context. But I want to let you know cleavage fracture is also a type of failure, and it is using an interesting word, but it's an engineering topic, okay? And then we're going to have the other big category of failure is called fatigue. So everybody is familiar with the fatigue. And then probably you don't feel so familiar with is the creep. Probably you're familiar with the sum of fatigue creep, yeah. And the other one, I think everybody know, is corrosion. So you're probably surprised that corrosion is type of failure too. Yeah. So if we just go with the kind of major division, we're gonna have fracture, fatigue, creep, and corrosion. But actually, why do I say fracture is a little bit more than just cleavage and ductile fracture? Because when you see from our catastrophe and all the examples that you found from daily life, although we have fatigue, although we have creep, but you will see finally fatigue and creep, they will both lead to a fracture. So that is why fracture is often mixed with failure for many cases, because fracture is, for most of the cases, is the final exhibition of failure. But in our context for this lecture, actually we're mainly talking about fracture in terms of brittle fracture and ductile fracture. Okay, so hopefully this makes you clearer about these terms. And now I'm going to give you some very famous examples of each type of failure. I assume, although now I don't see what you have discussed, but I assume you probably covered some of them. So I think everybody knows the Titanic, and that is a very significant failure before the World War II. And that is a typical cleavage fracture or brittle fracture, because the steel got a fracture under the seawater, and that leads to a significant catastrophe. So that is typical fracture. And for fatigue, the very famous example is this Aloha Airlines Flight 234. And this is, you can see from the picture, if you're interested in it, you can also click on the link and see some details. This is a really terrible catastrophe, but luckily I think there was not too many people dead. And but the plane was really kind of destroyed significantly, and the analysis after this catastrophe run was discovered is a fatigue of a metal part in the plane, and that really caused the really big loss of the structural integrity of the plane itself, and leading to this final failure. And for creep, I'm showing you a creep in a turbine blade. So probably you're not so familiar with this structure itself yet, but I think you know what is turbine blade. It is also related to very much to aircraft, and this is a very important component running at very high temperature. So that is why it is often related to creep. And this can be a very interesting interview question for material scientists or probably also mechanical engineer. Yeah, when you're going to a job and they would ask you what is the reason for such a cause, and most people will say, okay, fracture. If you say that case, you're making one mistake. Yeah? So this is, to be precise, it's creep. But as you can see, in the end, it is developing kind of fracture. And corrosion, you probably see this most often in our daily life. And I'm showing you a rust gears. And you can see with such a gears, the performance of this component will be significantly influenced. I mean, it's not developing a failure, it's developing a fracture. So here is the only exception that you don't really see two parts are developed from the gear, but this is also one type of failure. Okay, so we will start with the fracture. What is fracture? So here's my definition. Fracture is the separation of a body into two or more pieces in response to a load. So the key word here is load. That is why in the Ice Age movie we need the scrap, because that is the load provider to trigger the fracture. And in most of the cases we always need this load to get our final fracture. I just want to emphasize here again, fracture is the final expression of failure. What we learned from the movie is also fracture is led by running of crack, right? And that's why we're introducing you also two new terms. The first one is called crack initiation. How is that explained? So crack initiation is referring to terms. So first, it is referring the length. The length is pretty small, as you can see from this picture. So this is a crack, and it is a small one. And the second term it is referring to is the time. It should be at the very beginning of this whole process. That's why it's called initiation. And after the crack initiation, we know the crack is gonna run, and that term is called crack propagation. So you can see from the movie, probably still remember, the crack really runs and propagates like significantly. In the end, it is leading to the fracture, leading to the separation of a body into two pieces or even more. That was something we see from the movie. Yeah? And if we just go to our engineering world again, I want to go back to the tensile test. You probably remember from our last lecture. So these are two pieces of the tensile test after fracture. And you can see from the left-hand side, we have this typical development of neck. And you also see the fracture surface is something like, we call it cup and cone. Because here you can see this is looking like a cup and this is looking like a cone. That's why it's called cup and cone fracture. And this is a typical behavior of so-called ductile fracture. And why it's ductile, you probably remember we also showed you some curves from last time. If I can just draw here to you, the engineering strain curve, I think everybody still remembers that. And for the ductile fracture, we typically have the yielding, so the elasticity, yielding, and the plasticity, and the fracture. So here we got our fracture here. This is the ductile fracture. And on the other hand, you can see this is the typical brittle fracture. A very important characteristic of the brittle fracture is it has a very flat fracture surfaces. You can see there's nothing, there's no cup and core. So if you just also try to see what it looks like in terms of stress strain curve, you probably remember it usually goes like this, and then boom, fracture. So for most of the cases of brittle fracture, you don't enter any plastic deformation, so you don't see the yield point, and then you go to fracture. This is the reason for these very flat surfaces. And if you just try to make some schematic drawing, you can see on the most right we have the brittle fracture. That is also a schematic drawing of a tensile specimen. And in the middle is something we usually see from our tensile test. It is already ductile, but we usually call it moderately ductile. Because there's another type of ductile, it's called very ductile, because here you can see you don't develop something called the cup and cone. You develop really a connecting point in the end, and these two connecting points just get separated from each other. If you just zoom in to really the structure, you can really go to the two connecting atoms and you're just breaking their final atomic bond over there. As you can see, this kind of material probably doesn't exist in our daily life, but you can really produce them in the lab. And this is something you could see for pure copper or pure aluminum. So for pure copper aluminum, especially in single crystal form. Well, we have seen enough tensile tests. Now let's just have a look at in a bigger scale. We want to see something in our daily life in the engineering world. You have already given some very good example, as I see from what the group 1 did, as Heju just showed us. There's a cracked pipe. And so I'm here is showing you exactly a ductile and brittle fracture of pipes that could be used for many industries, especially for energy to deliver gases, oils, and so on. So as you can see, the first example here is a ductile fracture of a pipe. And just a few important features for you to show. So first of all, this pipe, they're separated, of course. You can see this is the cracks developed, but what's important is the whole pipe is still one piece. Actually, this is very important feature for us to consider in the engineering design, because it is important for the safety reason if your structure in the end is still holding its integrity. So this is called structure integrity. If the integrity is still there, so your whole structure is not that dangerous. You can imagine what makes a bomb dangerous, because after it is explode, it develops all the small pieces, and each of that small pieces is acting as a bullet. Yeah. So that's why we have a ductile fracture in a good mode to have one piece, or let's say in generally one piece. The second feature you notice is it has a very large deformation. So these curvatures are developing or indicating this kind of large deformation, and obviously they are ductile, they're plastic. And at the same time, let's look at the same pipe, more or less, but developed in a brittle fracture manner. You can see here we don't have one piece anymore. We have all these small pieces, and this is not exactly that small, but you could imagine if you have enough velocity for these pieces when it just got fractured, that will give a very dangerous scenarios, not just itself, but also the oil or gas inside of the pipe. Yeah. And of course, the second feature you could notice is each piece, they don't really have large deformation, they have very small deformation. And this is the very significant feature for the brittle fracture. All right, now let's get a basic summary about these two fracture types, ductile and brittle. So I'm giving you 3 characteristics for each fracture type. So first, let's talk about ductile. The first feature you probably have already noticed is ductile fracture is accompanied by significant plastic deformation. We have seen this from the, let me show you here, from the stress strain curve for ductile fracture, which is in such a type. And you also see from the fractured pipes and the significant amount of plastic deformation. And the second feature is something we didn't emphasize, which is about the crack propagation rate. You might consider why this is important. It is important because it's very decisive. If you just imagine what we had from the movie in Ice Age, if the crack of the ice is a little bit faster, let's say, our cute scratch will probably not escape from that catastrophe. Of course, if the crack is pretty slow with the speed that you even don't notice, then things will be very easy to recover, right? So as you can see for the ductile fracture, due to the plastic deformation we're having, and the crack propagation rate actually is pretty slow. But the very important, very practical important characteristic is the ductile fracture fails with warning. So what does that mean? The warning means the crack shows with a small crack initiation, and you can really see it, and you can see it develops, right? This is corresponding to the slow crack propagation as well. But something beyond that, for example, you don't always see something in service or so. But what you can also use as a warning can be easily, for example, here we can use the tensile strength as the crack initiation warning, and even for some cases people are using the yield strength, right? So as long as you see anything develop to their maximum force or maximum engineering strength, and in this case you would say, okay, at a certain point we might see a ductile fracture later on, right? So this is the three important features of ductile fracture. Let's move on to brittle fracture. As we have drawn before, still in the stress strain diagram, for brittle fracture we're having such type. So it is obvious to see there's little or no plastic deformation, of course. What I need to tell you is this is a statement based on macroscopic observation. So observation based on this kind of stress-strain curve from tensile test. Because locally, actually, if you just observe certain dislocations and observe certain atoms, there are always plastic deformation, even for brittle fracture. So this is a very even currently active field to identify the fracture or damage mechanism for brittle fracture. So you should know this kind of statement is on a macroscopic level. And the second feature of it is the rapid crack propagation. For example, the ice breakdown, that is the type of a brittle fracture actually for ice. And thirdly, which is the most, let's say, the decremental part of brittle fracture, it happens without warning. So it just runs, so the stress increases, the load increases, and at a certain point that you don't know, the fracture just happens without any warning. You cannot really make a precaution about it, and plus the very fast crack propagation. So that makes the brittle fracture actually is the most decremental fracture that existing in our engineering materials and structures. As human beings, we have already accumulated a lot of experience, a lot of failures in terms of brittle fracture to improve, enhance, shape our engineering practice in aerospace, in bridges, and in automotive, all these cases. That's why in a design, as one of the prevention rules, we always consider ductile fracture is generally more desirable than brittle fracture. Of course, the most desirable thing is we don't have any fracture, yeah. But if this is not avoidable, we prefer to have ductile fracture than brittle. As brittle fracture is such a significant and decremental failure type, let's first dive into brittle fracture and see what is going on there. We have seen the brittle fracture from the large component like pipe to the smaller ones of our tensile tests. Now we want to see how the brittle fracture looks like when we just look at our microstructure. So here I'm showing you one micrograph about the brittle fracture on the stainless steel 31304, which is common one used in the cookwares. And here we're looking at the rather small scale, not that small though, but you can see clearly the grains. For example, you see this kind of smaller kind of green lines indicating the grain boundaries. But the brittle fracture in this case is looking like these dark ones. You can see they're just going like that, especially here. What you notice probably the brittle fracture is exactly following our grain boundaries. Yeah, like this one here, of course, this big one. And we call this type of brittle fracture as the intergranular brittle fracture. So indicating the crack propagation is between grains. As you can imagine, we would have another one, which is called transgranular brittle fracture. So this is just like you can see with these dark ones, the brittle fracture is not going like along the grain boundary, but it's going through the grains. And this is one also stainless steel called the 316. As you can see, we kind of see the brittle fracture very flat when we just look at tensile specimen, but when we look at the microstructure, it is not that flat, right? Now we want to understand what is really the mechanism of the brittle fracture and why it is happening. Now let's get a brief understanding about the brittle fracture mechanism. And if you just recall what I've learned from the Ice Age movie, for a complete fracture, we need the 3 items. First, we need the scrap, which is the load provider. And then we need also the acorn, which is the crack initiation trigger. And lastly, we need time, of course, to have the final fracture or crack propagation to develop the final fracture. And the same applies here. Of course, we always have the load. That is easy to get. And here I'm showing you again tensile test. What we need to understand is how we get this acorn in our materials. And there are basically 3 ways to get this kind of crack initiation triggers for our crystals. Let's look at the first one. If we just imagine this is a small point, and here we're looking at the different grains, and we're looking at particularly in this grain. And probably you still remember from what we learned in our materials, there are always defects existing. It can be point like vacancies or line dislocations. But something also more significant is not any material is 100% pure. So you always have something like, we call about in the past related to interstitial elements and substitial elements. And something more significant, yes, is that you always have so-called inclusions and or something called precipitates. What you can understand is they're just something which does not belong to this kind of material. For example, when you buy gold, you cannot get 100% gold. What you get is only 99.99% of gold. So there's always some inclusions existing in your materials, and that can be somewhere at your grain and in the grain. And the dislocations and the vacancies, they will just try to accumulate at those foreigner, let's say, particles, and that will finally develop a crack initiation spot. And you can imagine the second point is the typical grain boundaries, because that is a place with a lot of dislocations and they're not that organized. And that is a place that dislocations always get stuck and get accumulated because they cannot move easily due to the slip system are changed. And when the dislocations accumulate a lot, you could imagine that will develop to a crack initiation. Yeah. And the third one is a little bit less common to see compared to the previous two. It is when the dislocations accumulate at the so-called trim boundary. So these are the 3 types of kind of, let's say, crack initiation triggers. And after the crack initiations are already developed, what we need is just to let it propagate, right? And here you can see, as we observed from the figure before, from the micrographics, and we see there are two types of crack propagation mode in the brittle fracture. One is intergranular, one is transgranular. So here today in this course, I'm not going to show you really the detailed mechanism for this crack propagation. So why your material is going intergranular, why it's going transgranular. Because this is more related to a little bit in-depth knowledge about grain boundaries, and also to understand all this kind of precipitates, even texture. You probably do remember something learned from the exercise from Lenchi in our first week. So in general, here I gave you the conclusions. The crack propagation for brittle fracture is relying on these two ways, and if you're interested in why they're going that way, and for a specific material, how do we decide, how do we predict if it's going that way or this way, so you're welcome to continue to the material science and engineering major for your bachelor, for your master, sorry, and then you will discover why. Here, I would like to give you a summary about what we have discussed on the brittle fracture mechanisms. As we discussed, we have three main components. I mean, load is always there. So the first point is on the fracture crack initiation mechanism of brittle fracture. So we know the crack initiation mechanism is due to the dislocation, accumulation at either grain boundaries, precipitates, or inclusions. So this is something you probably know, so we get that point, but why crack would initiate from those points? Actually, the reason is pretty simple, because with all this kind of accumulation, you would create a very high local stress concentration. And that is the final driving force for the crack to propagate. Yeah. And the second point, of course, is on the crack propagation. As you probably noticed from the figure just on the previous slide, the crack just propagates perpendicular to the highest principal stress via either transgranular or intergranular path. So I think from your solid mechanics lecture, you have already learned what is principal stress and what is just random stress. Yeah. So here we're talking about the principal tensile stress or principal normal stress. In tensile test, that is typically the vertical stress. Yeah. But in other cases, you need to apply the Mohr circle to get your principal stresses. Yeah, those are two important, let's say, characteristic on the brittle fracture mechanisms. And here I'm showing you one typical scanning electron microscope figures, so the SCM figures about fracture, the brittle fracture surface. As you probably remember from tensile test, it's purely flat, but we have kind of proof already with less resolution, let's say, to see the crack is probably not that flat. Here I'm just zooming in on the surface. You can see this is the brittle fracture, and you see the crack is definitely not that flat when you just look at it microscopically. But what you can see is it is very clean. So the material is almost like cut to two parts. All right, I think that is not that in-depth, but a rather sensible explanation about brittle fracture mechanisms. I hope you get it, and now you understand why brittle fracture is happening in engineering materials. Following our strategy, now we want to get some, let's say, quantitative description about brittle fracture. And with that, we can finally quantify it and hopefully avoid it. So for the brittle fracture, I'm introducing you one very important discipline, which is called fracture mechanics. So because in the end, this is a fracture problem, this is a mechanics problem, and you have learned the solid mechanics, continuum mechanics. Fracture mechanics is part of it. It's even a more advanced course that you probably have to meet it only at master level. And this mechanics branch is developed really to quantify brittle fracture and also part of ductile fracture. Yeah, so a few hypotheses for this development of fracture mechanics. So the first one is the fracture is a result of crack propagation, you get that point, and the crack initiation triggers are always existing in our materials, you also get that point. And the final point that we need to really get into here is the magnitude of applied tensile stress amplifies at the tip of these cracks. So that is what I called about the stress concentration, because of this kind of crack triggers this anchors in our materials. We'll get into that point. Let's say if you now try to think about, we want to quantify brittle fracture, and what will you do, right? If I just recall you something, sorry, let me get the pen. If I just recall you something about the stress strain curve, something that you learned so far about quantification, and we know brittle fracture just develops like that, and here we get a failure point. And a easy way to quantify it is just to take this stress, right? And that will be our kind of brittle fracture strength, right? Yeah, that is a very good idea. And that is also some engineering approaches people are taking. But I have to tell you, this is not a very sophisticated one. This is not the one that reflects the nature of this problem. The nature of this problem is exactly the last hypothesis is telling about. Let me just draw on our material, so I will make it rather simple. And let's say here we get our crack initiation triggers. So it's whatever. It can be a crack or a small, very ellipse, a very kind of flat ellipse. And if you just apply a load, so this tensile load we have there, that is okay. And you can imagine the stress that is finally triggering the crack propagation is at this point, right? And the stress here will be very much different from here and from there, right? This is something you can imagine, right? So that means that the real stress that is triggering the crack propagation is not the one we're going to get from our tensile test. It's this one at this local spot. So to quantify the brittle fracture, the first thing we need to do is to get the sense how to calculate this type of stress. And here I'm directly showing you some conclusion once again. So I'm not showing you the derivation of it because that takes quite some effort to do. But in the exercise, you will probably see how this is not derived, but verified. You will try to use finite element method to verify this equation. And here we can see exactly what I drawn. So here we have material, and in the center, let's say we have this crack initiation. And how do we characterize or quantify the stress right at the crack tip? So we call this spot as the crack tip. And this equation is telling us how this is resolved. So sigma m is the stress at the crack tip, and the sigma 0 is the nominal stress. And the correlation is the A is the crack length, and the rho t is this kind of, let's say, the radius that you could fit into your crack tip. So you can see this part is a geometrical expression of your crack. Yeah, so you can also imagine, right? The stress at the crack tip will be dependent on how your crack looks like. For example, here I'm looking at having such a crack. If you have a really long crack, so you can imagine the stress here will be different. Or if you have rather a round crack looking like that, so the stress here will be also, again, different. So this factor here is really trying to reflect your geometrical differences of the crack. And overall, this equation is finally connecting us with the crack that you applied as a nominal crack, with the strength that you applied, and also the stress at the crack tip. And if we just make another expression of it, is if we just take the sigma m at right the crack tip, and also the sigma 0, which you would observe at the end of your body, and you can see these two values, the ratio of it is called the stress concentration factor, which is this equation that I'm giving you here. This is just something for you good to know. And what is interesting is you always see when you just develop from the crack tip to your, let's say, matrix, the stress just gets such a profile, and it reduces from the high to low. And this actually gives you already a very good thinking for a design principle, let's say, or prevention rules to avoid brittle fracture. So what is it? Yeah, this can be applied to avoid sharp corners. Why? Because the sharp corners will have a very small, previously this called the rho d, and here it's r, right? It is this radius with the fillet. Yeah, because this radius will make your geometrical factor very high, and that will just amplifies your nominal stress to the stress, local stress at the crack tip. Here you can see from the figure how this would develop. So that is a way for us to characterize the local stress. Okay, that is good. And now we want to know how much this local stress would reach to finally trigger the crack propagation, right? I mean, we get the crack initiation always there because we have the defects, we have all these impurities in our material that will always develop various types of crack initiation triggers. But the stress always needs to reach a certain level to get the final crack propagation. How to describe this? And here I'm again giving you a final conclusion without a derivation. This is not good, I know, but to derive it is really taking us a long process, and that's why you will get all this knowledge if you just go to your master study, or you kind of go to this topic as your really major in the future. And what I can tell you is derivation is the knowledge from several generations, and it's very beautiful. And here I'm telling you the critical stress for a material to trigger the crack propagation of brittle fracture is given in such equation. So the sigma C is the so-called critical stress. And what you can see here, A is the crack tip, is the 1/2 length of the internal crack. So this is the A. We have C, and pi is geometrical constant. And then we have two new material-based parameters. So the first one is the modulus of elasticity, and the second one is so-called specific surface energy. So what do these two mean? So you know the elasticity, right? So with this kind of a proportional correlation, you can imagine if your stiffness, your elasticity is high, you would always get a higher critical stress for the crack propagation. And that is easy to understand, right? The second one is called the specific energy, surface energy. This energy is representing the energy that you need to create a unit surface. Basically, you just break a unit surface of your material, and this parameter is very much material dependent. I cannot show you the derivation, but I can show you a kind of imperfection, a implication about this thing. You can easily imagine this one is correlated to the so-called binding energy, as we just talked about the atomic bondings. Yeah, you see the fracture is nothing but a separation of two atoms in the end. You just separate them large enough, and they will never be bonded again. That's a crack, right? That's our fracture. So that's why if we just want to create a crack, we're creating new surfaces, and deep down we're trying to separate the bond, and we're trying to overcome this kind of binding energy between the atoms. And in the end, you will develop your fracture. So this gamma S is highly correlated to the binding energy over there. I hope you get the sense of it. Of course, if we have a higher binding energy, that is good for us, for our material to resist crack propagation. Yeah. So this equation here, it's an important one for you to know and to get the sense of it. A important feature is this critical stress. It is important to notice it is geometry dependent again. So the critical stress that you need to trigger a crack, to trigger the crack propagation, depends your initial crack, your kind of a crack initiation, the length of it. I hope everybody get this point, yeah, because the strength is, as we showed before, is dependent on your geometry. And three important conclusions here. Yeah, our materials naturally have numerous cracks with different lengths and orientations, as we just discussed before. And if we want to trigger crack propagation, we need to make sure the sigma m that we just derived, how to calculate it, right? This is let's say, an intrinsic value. This value should be bigger than the sigma c, which is sort of intrinsic value. So it is material dependent. It is also the crack geometry dependent. And this only happens for those cracks with the lowest sigma c, right? Because if the crack is larger, for example, the A is larger, what the required sigma c will be lower. Yeah. And in the end, the largest and most highly stressed cracks will go first. And this is the conclusion of the previous 2 points. And with that, I think we can finally introduce the main term of today, which is called fracture toughness. As we have talked about how to characterize stress when you have a loading at a critical point. And we also talk about what is the critical stress a material at a certain crack should have. And now we want to really get the intrinsic characterization of our material property to resist the brittle fracture. So this concept is called fracture toughness. The definition of it is it's a measure of a material's resistance to brittle fracture when a crack is present. So as you can see here, this toughness is different from the toughness that I just showed you when we have the stress strain curve. Probably remember, yeah, this part is also called toughness. So you need to be careful with these two terms. So that is called toughness, and here is called the fracture toughness. So these are two different terms. And how is this defined? So it is defined first, it's called KC, so C means critical again, KC, and it is an equation of Y, sigma C, and times square root pi A. So first, what is Y? Y is a dimensionless parameter. So this is just I can tell you it's a correction parameter because we want to use the fracture toughness as a material dependent quantity, but somehow when we try to measure it, for this course I cannot show you all the experiments to measure the fracture toughness. But when we measure it, we always need a certain geometry. We cannot go to the really unit crack. So when we have a certain geometry, and the certain geometry always have a shape factor on the KC value, and what you can take into conclusion, let's say, is for the planar specimen. So let's say a flat specimen, the crack, when the crack is much shorter than the specimen, so that's actually the Euro case, we can consider Y is equal to 1. So just take it as a conclusion. I cannot really show you the derivation of it. But what you need to see is why this equation, we're getting the sigma C here, and we're getting this square root of pi A here again. If I just bring the critical stress definition here, you can probably see the reason of it. As I said, the sigma C is an intrinsic value, but it is reflecting both the material intrinsic and also the crack. And we want to have a value is completely on the material side. We don't want to know how big is the crack, so it's small or large. We just want to know if we have such a material, we know, oh, its resistance to crack is like that. So that's why you can see what we did here is very simple. Basically, we just took the square root of pi A. We took the geometrical part out of it, and then you keep only your material intrinsic property or intrinsic characteristic to resist crack. All right, that is the definition of fracture toughness. I think you are all clear with that. And that is also our major concept for you to get for today's lecture. And as I said, so we need to measure the fracture toughness. That is not an easy job, first of all. And secondly, this is very much correlated to what type of test you are doing. So as you can see here, we have this opening or tensile mode. When we have a crack looking like that, we're trying to open it, and we want to see at what stage this crack will get propagated. This is one mode, we call it mode 1. And you can also see we have this so-called mode 2, so we have a small crack there, and we want to apply a slide mode. So basically you can see here it's sharing. So over there it's tensile load, and this is a shear load. And that will give you another value. unfortunately, another value of fracture toughness. And more if you just apply still a shear, but not in this longitudinal way, but more in a horizontal way, or you're doing a tearing, you can see it from here, and you will get another fracture toughness value. And for a common material, you can imagine this three would be different. What you can try to do is, if you just have a piece of paper and you want to verify this difference between mode 1 and mode 3, so you can easily imagine the mode 3 would be much easier for you to just tear and paper to two parts. That's why we need to specify what kind of fracture toughness we're talking about. That's why when we talk about the Kc value, we always try to indicate before the C with the Roman number 1, 2, 3. So don't read it as KIC. It is K1C. So this is the mode 1. So that is the most often used mode or tested mode for fracture toughness. And this is a kind of very brave overview for our material map again. So you have metal, ceramic, polymer, composites. You can see we have metal with the highest, almost highest fracture toughness due to the reason they have, of course, higher E modular. If you remember the equation of fracture toughness from the atomic structure point of view. And it also has a higher surface energy. And the second is composite, of course, for this rather brittle material, let's say ceramic and polymer, they would feel with a smaller fracture toughness. Now you have got the point of fracture toughness, and you know it is a completely material intrinsic value. So finally, here we can establish our crack growth or crack propagation condition, which is when the right-hand side, these are reflecting, let's say, the extrinsic part of our loading or our geometry feature of the crack, bigger than the material intrinsic value, which is this K1C or whatever fracture toughness you're talking about. And as we want to just say, not talk about the material design, we're talking about design of our component of our loading. And we have always a constant K1C, and there would be two scenarios for us to do the design. The first one is we have the constant K1C, and we also have the constant flaw size, which is the crack size in our material. And then you could say, if we want to design against fracture, we basically need to have a little bit smaller critical stress, right? And that is finally correlated to, let's say, your loading. Yeah. So this is typical for your loading design. Don't go over to the fracture limit, but always stay with the no fracture part. And of course, the second scenario is when you have the constant K1C and you have a constant stress level, right, like that. And the loading is always fixed. And now, how can we avoid a fracture? Basically, you need to make sure in your material you don't have very large flaws, right? That's why in many cases for our product, before they go to into daily life, they're always detected with the ultrasonic machine, right? Now you know what they're detecting. They're detecting the largest flaw size. They need to make sure the largest crack flaw size in the material is not bigger than a critical value. All right, so that is all about brittle fracture, and we will stop here today. So tomorrow we will continue with the ductile fracture. All right, everybody, I wish you a good day and see you tomorrow.